And we're back. Go ahead.
Alright, so hi, I'm Abby Swanson, and my movie was Interstellar, so this is about the mathematics of Interstellar. First, a little plot summary. So, Interstellar is set in a future time period where, the Earth kind of went through almost like a civil, a huge, World War III, where all of the crops started to die, the soil couldn't handle harvesting all the crops, so food was down and everyone was starving, and then what the government's plan was to kind of eradicate, this way? Okay. The government, way to get rid of all these starving people were to just drop bombs on them and to kill them, because then they have less of a population that they need to feed. And so this kind of takes place about 30 to 40 years after this whole war. And so the main characters they don't really talk about last names or first names, they kind of just give full short names. So Cooper is the main character, and he is a farmer, and the only crop they can grow is corn, because it's they're in a giant dust bowl, part 2. So he's a farmer, as well as he was an astronaut. He used to pilot spacecrafts for NASA. This was before NASA was disbanded. Murph is his daughter, and this is actually the older version, because there's 2 versions of Murph. There's the child version that we see when Cooper is still on Earth, and then because Cooper goes into space and he does a lot of time travel, and because time is relative, so where he is it might be an hour, but on Earth it was 20 or 30. So this is Murph when she's older, and this is what the version of her that we see for most of the movie. And then this is Dr. Brand, who was an astronaut that worked with Cooper and went on his traveling with him. And then this is Professor Brand, which is Dr. Brand's father, and he was a professor at NASA when Coop was still piloting for them. And then after the reason that NASA disbanded in the movie was that the government asked them to drop these bombs on the starving people, and he was no, we're not doing that. So they technically defunded them. But then a couple years after this whole happened, they found what's called a wormhole had appeared just outside of Saturn, and they were like, oh, okay, well, we kind of need to look at that. So they kind of reformed NASA and brought back all of these people like Professor Brand, and so his kind of life work was figuring out what's in this wormhole, and so they sent probes in there, and they found it led to another part of the universe, kinda, because they do state that they don't really know where it led to. It could be a part of our universe, it could be a whole nother dimension, it could be a whole nother galaxy, they don't really know. But they found 12 livable or potentially livable planets through this wormhole. And so what they did is they sent out 12 scientists in 12 different space shuttles, each to go to their respective planet, and then report back to Earth on things like livable conditions such as water or organic materials and different chemicals that we would be able to survive, like oxygen or nitrogen. And then so this is 10 years after is when we kind of see Coop and Murph, and they kind of stumble upon NASA's secret hidden, it's almost like Area 51 that they stumble upon, and Cooper is recruited to go on an additional mission because 3 of the 12 planets have been deemed potentially livable for the human race, because the Earth is dying and humans can't survive much longer on Earth, so they're going to try and move humanity to a new planet. And so Cooper, along with Dr. Brand, and then there were 2 other scientists, but they weren't a big deal. I could spoil it, but I'm not going to. They set out to go through the wormhole and to these new planets, and to get to Saturn it takes only 2 years, but once they're through the wormhole, just going through the wormhole itself sets them up that's 5 years on Earth. And then when they go and visit the first planet, an hour on that planet is 7 years on Earth. And so what happens when they get down to that planet is they find that the professor that went originally was actually dead, and there was a malfunction in some of the equipment, like the transmitting equipment. And so that planet wasn't actually livable. It just was deemed livable 10 years ago, and then everything got destroyed and the professor had died. But then they end up getting stuck there for a while, so when they go back up to the station where the other two scientists were hanging out, just kind of like, because what they do is they travel in like almost like a big like space station, and then to go to the planets they call it the Ranger, which is just like a smaller space shuttle. Like 23 years have passed, so that's how we see Murph as like an adult now. And then they have to go to the other planets essentially to like figure out what's deemed livable and where they can move humanity. And there's two plans that they have set up for like when they find the planet that is like perfect for humans. And it's plan A is the space station, or like the space command center on Earth is being turned into almost like a huge rocket. So they were going to pack all the scientists into the space station and then shoot them through the wormhole just to kind of like relocate. And then plan B was, if they're not able to do that, is on the space station that they took into space, they have 5,000 fertilized eggs. And so they would get to camp on like this planet, kind of set up, and then they would start fertilizing eggs and like surrogates, and to like slowly rebuild the population from those original 5,000 eggs on this new planet. And then everyone on Earth was just gonna die. So it was just kind of lose-lose. And I don't know, you can't really see it on the edge here, but I gave this movie a 5 out of 5 because it blew my mind. It's also 3 hours long, worth every second. This is only like the first hour that I described, but it is an amazing movie. 10 out of 10 would recommend. You should go for it. But the thing I struggled with is there's no actual math in this movie. It's just a lot of science. So I kind of had to work off of that and figure out. And Kruger kind of recommended me to focus on the wormhole that they travel through. And so to kind of understand like the time travel of it all, I first had to look at Einstein's theory of general relativity, which was first published in 1915. And first off, he formed the theory of special relativity 10 years before, in 1905, which there he kind of stated that mathematically he proved that space and time kind of form they like merge together to form one continuum, which is known as the space-time continuum. But with the theory of general relativity, he proved that massive objects cause a distortion in the space-time continuum. So you kind of can see it here. So when he means like massive objects, he means like stars or planets or other things out in space. And the thing that made it so like mind-blowing and so like important was that Einstein didn't take, like before this, they had always taken gravity in as a force, where Einstein took it in as a linear factor, which is why he could kind of come up with this grid system. And then he kind of like proved like his version of gravity, because like as something travels across the space-time continuum, it'll hit one of these distortions caused by a massive object. And if the object, like such as the moon, is smaller than the object that causes distortion, it'll get caught in the divot that it created and just start circling, which kind of creates the orbits there. And then so what a black hole is where I kind of explained it yesterday too, is black hole can be caused by two things that I found, and it was either they found like some at the Big Bang, they were like, okay, well stars and planets were created, so why couldn't a black hole? And then as well as the collapsing of a star, so the life of a star is it gets bigger and bigger and bigger, and then finally it gets to the point where it can't contain itself, and so it collapses back in on itself and creates, well, like in relative to space, a smaller, very, very dense version of itself, and that it stretches the space-time continuum so much that it creates like such a huge divot that nothing can escape from its gravitational pull, not even light. And like Ryan kind of explained it yesterday, like inside a black hole there's the singularity, which it's kind of tough to see, but there's a tiny little dot, and then you have the event horizon, which is kind of the point of no return when it comes to a black hole. Is not even light can escape from it, and then kind of everything around it is the things being sucked into the black hole. And so what like a wormhole is when Einstein theorized this in 1805 or or not 1915. In 1916, an Austrian physicist, Ludwig Flamm, was reviewing some of these theories, and he kind of came up with an additional viewpoint on it, and he theorized what are called white holes, which are essentially just the reverse of a black hole. So a black hole goes this way, a white hole goes this way. And then many years later, and I think it was 1935, Einstein and another physicist named Nathan Rosen were using this observation as well as the theory of general relativity to propose the existence of bridges. They termed it Einstein-Rosen bridges, more commonly known as wormholes. So what a wormhole is you can kind of see the space-time continuum when it wraps around like this. And so in technically space-time travel, you would originally have to get from point A all the way around to point B. But what a wormhole does is it creates a black hole on this side and a wormhole on this side come to connect, and it almost creates a shortcut. And so I'm not going to do my demonstration because it pretty much explains that, but it pretty much creates, like they said, a shortcut, and that's what comes up in the movie Interstellar, kind of near Saturn, is the entrance to a wormhole appears, and then it shoots them into another galaxy where those planets are. And so when it comes to wormholes, everyone's well, this is time travel, it's crazy and it's awesome. But the thing with them is mathematically they've been proven to be able to exist, but physically scientists have never found one before. So they're pretty much saying everything says they could, but they haven't physically found one yet. Additionally, they're projected to be 10 to the negative 33 centimeters wide, so very tiny. Can't really fit a human rocket. But the thing is, as the universe expands, everything around it expands too. So kind of we said stars expand, it is very probable that a wormhole could expand too to fit to be travelable. The other thing that they would propose too is that they're extremely unstable and that they have a very high probability of collapsing in on themselves. And so again, that's a whole another thing that makes it, you can't really time travel through them. But the thing that they did propose was to insert, they call it exotic material into a wormhole, which an exotic material has a high negative energy as well as a large negative pressure. So that would kind of counteract the instability of the wormhole, and potentially stabilize the bridge between the two. So that's the theories. And so again, I kind of the math on this was kind of ridiculous, and I read a bunch. I tried to get through a bunch of papers, and I got stuck at paragraph 2 on every single one of them. I got through the first equation, and it was it was kind of crazy. So the first equation that I looked at was Einstein's equation for the space-time distortion, and this is just kind of for any general planets, stars, and I guess wormholes or black holes too. And so the different variables of it are the Ricci tensor and the Ricci scalar, and that I tried to figure out. I was okay, what are those, right? And so I looked up, and they belong to it's called a Riemannian matrix. And I was okay, what's that? And it took me to a whole nother subcategory of geometry called Riemannian geometry. That was a whole nother. But to my best understanding, those two factors, so that's going to be R with base AB and R, those two are kind of the estimate of the curvature of the distortion caused by the object. And so those kind of take into account. And then G with base AB is the line matrix, so that's the linear factor of it. And that's kind of why Einstein, it was just his different look on it. That's why it was kind of so groundbreaking. And then on this side, G is the factor of gravity, the constant of gravity, so 9.8. C is the speed of light, and then it's kind of cut off here, but T to the AB is the EMT, or the energy momentum tensor. And that is the variable that describes the amount, type, and distribution of energy and matter in space. So that's kind of the object itself and kind of taking that into account. And so this, again, kind of calculates the whole curvature and the distortion caused by massive objects in the space-time continuum. And then the next equation that I found, this was paragraph 2 right here, was the Morse-Thorne metric. And so Kip Thorne is a scientist in the 80s, and he kind of popularized like this whole idea of like the space-time continuum, even though Einstein was the one who came up with it. And then Mike Morse was his grad student, so they kind of came into this. And so essentially this equation is more specific to a wormhole, whereas this one's just kind of for any distortion in the space-time continuum. Yeah, so this one, and it describes it in spherical coordinates. And so what these are, so this is, again, a lot of these variables I could not find because they don't exactly, like in mathematical papers, they don't tell you like this variable equals this. They kind of just, like I had to go through 3 just to figure out these ones. So if you can see this right here, this kind of like, so I don't even know what that's called. So the R, which is what E's raised to, is called the redshift function. And that function describes any finite existence of like the event horizon that could cause an event horizon. So that's a variable that it calculates the event horizon. And then B to the R is the shape function. So this is the part, like that's the variable that calculates like the shape in spherical coordinates of the mouth. They call it the mouth of the wormhole on both sides. And then R in like any of these variables is called the flare-out function, which pretty much just describes the throat of the wormhole, which is like this part right here. And so this is essentially that, but this one is more specific to wormholes as it has 2 sides that they have to take into a factor. And it's based off of that original equation. And that is it. Do you have any questions?